Well, welcome to Fall 2020, Mathletes. We're going to go ahead and start this first lecture with some review. In fact, that's pretty much going to be the main point of this first lecture. There's a few things that I want to make sure that we review at least quickly before we start this semester. So, I figure we'll go ahead and get started with that. What we're going to start with first is covering how to deal with roots. And so there's a few things we're going to be doing when it comes to roots. I'm going to focus primarily on square roots because that's what we're going to be dealing with most this semester. The things that we're going to cover with roots are going to be simplifying, and then all of our operations. We want to be able to add, subtract, multiply, and then division's the thing that's going to be handled a little differently. Division's actually handled by rationalizing the denominator. And so it doesn't, it definitely plays in with multiplication as division usually does, but it's really not quite the same thing. And also, addition and subtraction are pretty much the same thing. So this is going to get chunked up real nice here. Okay, so let's go ahead and take a look at what we got. I may erase this stuff here in the corner, just depending on if I need the space or not. But nonetheless, let's go ahead and take a look at an example. So, let's say you're walking down the street, you're walking down a dark alley, and someone jumps out from behind a dumpster and demands that you simplify the square root of 72. So you can see what kind of a pickle you're in there. So let's just go ahead and walk through the process, because clearly under these kinds of conditions, this could save your life. So when you're trying to take the square root or simplify a root from something, really what you want to do, the one technique that pops up probably the most is using a factor tree. And so we'll start by building our factor tree. And a factor tree is built this way. I'm going to take and build two branches off of this 72. Now, what I'm going to try to do with this is I'm going to try to find two numbers whose product is 72, two whole numbers, and neither one of them can be a 1. So in this case, we could choose a few different things. We can choose 8 and 9. We can do 12 and 6. We could do 2 and 36. Any of those will work, and you'll still get the same answer at the bottom. So any two that work for you. I'm actually going to start with 8 and 9. Right? Because that's probably the one that jumped to most people's minds just starting out. So 8 times 9, it does equal 72, but neither one of these are prime numbers. We need to break this down to only prime numbers. So we can continue moving down each one of these columns here. 8 can be written as 4 times 2. Now 4 is not prime, but 2 is. So I'm going to circle the 2 so I don't lose it, because I want to keep track of these primes. And then 4 is 2 times 2. So you notice I just kept breaking down the number as I went. And then once I have all primes at the bottom, I like to circle those, especially when they get when it's a big number you're factoring. Sometimes those things get really kind of crazy, and you don't want it to. So it's best to actually circle the prime numbers as you run across them. And then 9 is 3 times 3, and 3 is prime, so that means I can circle both of these. Okay, now once we have this much, what we want to do is sort. We want to see what can come out of the root and what can stay inside of the root. So looking at these, since it is a square root, what I'm going to be looking for is pairs. If it was a cube root, I would be looking for triples. If it was a fourth root, I'd be looking for 4 of a kind. But in this case, it's a square root, so I'm looking for anything I can pair up. So I can pair this, right? 2 and 2. This other 2 doesn't have any friends, so he's going to stay exactly where he is. And then I have a pair of 3s. Okay, now once I have this sorted, once I have these identified, all of my pairs are identified, that's how we decide what's going on. So the square, because really what I'm doing is taking square roots as I go here. A pair of 2's, if I multiply them together, is a 4. And so this right here actually represents the square root of 4, which is 2. So 2 times 2, when it's inside the root, ends up coming out as a single 2. So pairs come out as a single. So I have a pair of 2's, that means I can write a single 2 on the outside. I have a pair of 3's, and the same thing will happen here. 3 times 3 is 9, so what I'm really doing here is taking the square root of 9 and getting 3. So that means there's a 3 on the outside, and these two things will be multiplied. And then anything you have left over goes inside the root. So this 2, this little guy right here, let's see if I can, this guy is all by himself. He doesn't have any friends, and so he's got to go inside the root. And then to write down your final answer, we just need to multiply out anything that I have left. So 2 times 3 is 6, and then the square root of 2 doesn't need to be simplified, so I'll write this as 6 root 2. Now, I want to point out a little bit more explicitly what's going on here. Because all this stuff right here that I just did is a shortcut to what's actually going on. Really what just happened is we broke this whole thing down. We said the square root of 70, oops, that's not a 72. Let's try that again. The square root of 72 is equal to all these numbers multiplied together. 2 times 2 times 2 times 3 times 3. That's really what's going on. And what I'm doing is breaking this up. I'm going to take these two and these two, and I'm going to look at 2 times 2. Actually, let's switch that. Let's back that up. Where's the button? There it is. So instead of these two, I'm going to pick these two because that way I can leave that one looking like it's supposed to. So once we have that, really what I'm looking at is the square root of 2 times the square root of 2 times 2 times the square root of 3 times 3. So I'm breaking these up in sections. The square root of 2 can't be simplified, but this is the square root of 4, and this is the square root of 9. Square root of 4 is 2, the square root of 9 is 3. And so this is the square root of 2 times 2 times 3. So this is where your 6 comes from, and then your root 2 is the one you can't simplify. Right? So that's actually what's going on there. It's sufficient for you to just be able to use the factor tree as you go. Right? So basically whatever gets you the right answer, as long as it's not cheating, use it. Okay, so that's our first example here. Now, let's see here. I'm going to try to... there we go. I'm going to clean this off, and we'll look at the next example. There we are. All right. There's my pencil. Okay, so let's look at the next example here. So let's say I have the square root of 36. Okay, now if you already know the square root of 36 is 6, by all means, just write down 6. We know the answer already, but I'm going to walk you through the process because sometimes you don't realize something's a perfect square, and it looks a little weird when you do the factor tree. So let's go ahead and do that. So the square root of 36 is 6 times 6. Neither of these are prime, so we can keep going. 6 is 2 times 3. Oh, both of those are prime. That's good. And 6 is still 2 times 3. And so now we just need to sort and pair things up. Right? So here's my root. And let's see, I have a pair of 2's here. So a pair of 2's comes out as a single 2. I have a pair of 3's here. And a pair of 3's comes out as a single 3. I don't have anything left to put in there. Um, so what do? You just leave it. What was that? You just leave it. Yeah, that's right. You just leave it. Um, I'm not going to worry about that root. If there's nothing in here, then there's no reason to write it. So my final answer is just 2 times 3, which is 6. Right? So it's fairly straightforward. Sometimes these things get pretty ugly. Let's look at a nasty example. In fact, when we look at this, what I'd like you to do is when I write down the problem, go ahead and pause it and see if you can work this one out on your own. Um, let's see here. Let's go ahead and work out the square root of 1024. So go ahead and pause. Okay, so if you're done pausing now, if you unpause it, let's go ahead and walk through this. So I need two things that multiply to give me that. Oh my goodness, that's a big number. That's not on my times tables. Well, let's see here. This thing is even. Okay, so even means 2 goes in. So I can write that down, so that's good. 2 goes in, but I don't know how many times. So I'm going to work that out. And what I'd probably do is this on the side, or use a calculator. Although I would encourage you to not use a calculator at this point because it's really best to get a feel for the arithmetic. But if you do the division here, you end up with 512. Okay, so 2 is prime. So that's my first prime. And now I have to, well, let's see, is 512 prime? Let's see, it's even, so it can't be prime. Oh, and it's even, so that means 2 goes into it again. Okay, so 2 goes into that, and then I'm going to have to do the division here. Let's assume I did it, and it came out to 256. Okay, so now 256, well, I'm not seeing that either. That's not on my multiplication tables. Let's see, what can we do? 2 goes in. That's right, 2 goes in. So I'm going to use that even number thing again, because that's actually quite convenient. And then I'm going to go ahead and divide, and what I'm going to get is 128 on the other side. You may have to do this the long way, right? It's okay if you don't know what multiplies out to give you that number. Just figure out two things. You have a calculator, and just use a little common sense. You don't have to know it right away, although it does help. Let's see here. Now 128, oh, it's still even, so that means I got another 2 in here. Okay, so 128 is 2 times 64. Okay, so I'm running out of vertical room here, so I'm going to actually just switch directions. So 64, now that's back on my multiplication tables. That's 8 times 8. And then 8 is 4 times 2, and 2 is prime. And then we get a 2 times 2, and that's prime. And you notice I've completely switched directions on this thing because I ran out of room. Feel free to do that. Just make sure you keep track of which tree you're on. And then we have to work out this one. So that's 4 times 2 and 2 times 2. Whew, that's a lot of 2's. This is a really even number, isn't it? Okay, so I got all my primes found. And now I just need to start sorting. So let's see. Ooh, you know what? Let's do this. I'm going to go ahead and get rid of that. And actually, let's go ahead and get rid of this too. And that way I'll give me enough room. Oops. There we are. All right, so I have my root. Let's try it again. There we go. So I have my root here, and now I just need to start sorting by pairs. So I have a pair of 2's. So that's a single 2. I have another pair of 2's. That's another 2. I got a pair of 2's down here. That's another 2. Oh, I'm going to run out of room again. Let's go ahead and that is not what I was trying to do. Hold on. You'll have to forgive me. The whiteboard I was using kept crashing, so I had to start using MS Paint. And I'm still getting used to it. So let's go back here. So brushes, there we go. Okay, so we have 3 of them. Let's see, I have another pair of 2's here. So that's another 2. Oh, and then finally, my last pair of 2's here. And if I check over this, I don't have any other primes hanging out there, which means I don't even need the root. So this ends up being 2 times 2 times 2 times 2 times 2, which is 32. Right, so that one ended up being a little bit more work, but it's still about, excuse me, just factoring everything out and seeing what pairs you have. All right, so let's go ahead and look at the next example here. All right, so let's see here. Let's go ahead and switch back to that. And, you know, sometimes you'll get things like this. Let's see here. Yeah, we'll do that. Sometimes you get stuff like this, right? Square root of 5. So remember again, when you're looking at these things, what you're looking for is pairs. And what that exponent of 5 means up there is that you actually have 5 different x's being multiplied together. Okay, so if I go ahead and use my tree, and by the way, this isn't the way I'm going to want you to do it. We're using this to find a better way to do it. Let's see here. What multiplies to give me x to the 5th? Let's see. X squared times x to the 3rd gives me x to the 5th. X squared is x times x. And you notice I can't simplify those x's anymore. So what I'm going to do is go ahead and just circle that. X cubed is x to the 3rd times, x squared times x. X is prime. Actually, yeah, that's fine. And then x squared is x times x, and that actually gives me another pair. And so you notice this is still just the 5 x's I was just talking about. And we're looking for pairs. So you can go ahead and sort this out that way, but let's look at what our answer is and see if we can find a better way to look at it. So let's see, I have x times x, so this turns into 1x, this turns into another x. And so that means I have 2 x's on the outside, which is an x squared. And then I have this one lonely guy sitting here waiting with no partner, right? And so we end up with x squared root x. But I want to point this out. Let's see here. I'm going to erase this. Not worrying about all of this for a moment. Let's actually take a look at this again. So x to the 5th, I already know how many x's I have. I have 5 of them. I don't need to do a factor tree for that. And because I know I'm looking for pairs, I can just ask myself, how many pairs of x's can I get out of these 5 x's? 2. That's right, I can get 2 pairs, because if you look at them this way, right, I have a pair of x's here, I have a pair of x's there. I can see them. 2 goes into 5 twice. Okay, so that means I have an x squared on the outside. Now, after I've paired those up, how many x's are left over? 1. That's right, there's 1 left over. So I can just write it down. So when you do this, really what you're doing is you're dividing 2 into 5, which goes in, let me switch the color here. It goes in 2 times, and then you have a remainder of 1 here. right? So you have quotient and remainder. So it really is division. Okay, now let me go ahead and get rid of this. Now let's go ahead and look at another example. Okay, so this is another one I want you to pause and see if you can use that reasoning that we just used. And I'm hoping that a lot of this is review for a lot of you, but see if you can use the reasoning. There it is. Okay, let's try this again. But see, let's try this one more time. Okay, so see if you can use that reasoning to simplify the square root of a to the fourth b to the seventh. Okay, so go ahead and pause the video, see what you can do with it, and then go ahead and start the video up when you're ready. Okay, so let's go ahead and start sorting. Now, we can handle these one at a time because one of the properties of square roots is that you can split them, right? I can look at this as the square root of a to the fourth times the square root of b to the seventh, although I don't have to split them to actually do it. I just need to simplify them one at a time. So I'm going to write down my root, and then I'm going to start sorting what goes in and what goes out. So I have 4 a's here. How many pairs of a's can I get out of that? You can get two. That's right, you can get 2 pairs, right? And honestly, it's just saying 2 goes into 4 twice. Is there anything left over? No, there's no remainder. That's right, we have a 0 remainder, which means that I'm not going to be writing anything inside the root. So I have 2 pairs of a, and so that means I have an a squared in here. I don't have any a's left over after I pair them up, so there's nothing in the root that I'm writing down. Now I'm going to turn my attention to the b to the seventh. So I have 7 b's here. How many pairs can I match up? 3. That's right. There's 3 pairs, right? And you can think about it this way. 2 fits into 7 3 times. I'm not worried about the remainder just yet. I just want to see how many times it fits in as a whole number. So that means I have a b to the third here. Do I have anything left over? Yeah, b. That's right. There's b left over. And so b stays inside the root. Right? And so that's really how we handle this stuff. And when there's numbers also, we end up doing all of these things together. So if let me go ahead and clear this here and clear that off. Let's go ahead and look at one more. And let's see here. Let's say I want to look at the square root of 100 a to the 13th b to the 9th. Okay, so here's how we handle these. Now, first of all, actually, let me pause there for a moment. See if you can work this one out on your own. I'll tell you this much. You handle one piece at a time as you go across. Okay, so go ahead and pause and see if you can do it, and then we'll start back up. Okay, so let's go ahead and start looking at this. So this is, I don't know, this looks like it might be kind of big, so I'm going to leave a lot of room here for sorting. First of all, 100. I think most of us know the square root of 100 is 10, but if you needed to, go ahead and walk through the whole factor tree. Oh, this is 10 times 10. This is 5 times 2. This is 5 times 2. Right, I have a pair of 5s and a pair of 2s, so that means I get 2 times 5, that's 10. Right, no numbers end up back in here. Okay, now we have the numbers, or the variables to take care of. We've handled the numbers. The square root of a to the 13th, well, 2 goes into 13 6 times, so that means there's an a to the 6 on the outside, and I have 1 left over, so that means I have an a left over inside. B to the 9th, 2 goes into 9 4 times. So this is a b to the fourth. This is a b to the fourth, and I have one of these b's left over. And so when I've simplified this, I end up with 10a to the sixth b to the fourth times the square root of ab. Oh, excuse me. Okay. So that pretty much wraps up most of what we need to do here as far as simplifying goes. Okay, so now we're going to take a look at adding and subtracting. Now, adding and subtracting is pretty straightforward. It's very much like polynomials. You're collecting like terms, only instead of like terms, we're actually calling them like radicals. And then multiplication also behaves like polynomials. We're still doing things like FOIL and all of that stuff. The only thing that you do in addition to that is you have to simplify along the way, which is why we started with that. So let's take a look at an addition slash subtraction problem. So let's say I have this. Let's say I have the square root of, oops, this is probably going to be a lot easier if I turn on my pencil. There we go. Let's try this again. Okay, so let's say we're looking at simplifying the square root of 70. Oh, that's not a 75. Square root of 75 plus the square root of, yeah, so that's going to have that, 125 plus square root of 9 plus, oh, let's make one of them minus. That sounds like more fun. Minus square root of 27. Okay, so let's say we're looking at this. So the idea is that we're looking for like radicals. Nobody looks alike here. What we're really looking for are things that look like this, right? I have like 3 root 7 plus 5 root 7. And let's see, that means I have 3 of them here, 5 of them here. I have 8 root 7s. And you notice it's just the root is just behaving like a variable. It's just telling you how many of those roots you have. Now over here we have a problem because nobody's a like radical. So we need to simplify to see if we actually have any. Sometimes you get like radicals, sometimes you simplify and you don't. But you do need to simplify no matter what. So if we go through and simplify square root of 75, that's 3 times, oops, let's try that again, oops, 3 times 25, 3's prime, 5 times 5 is 25, so I have a pair of 5's. So square root of 75 is 5 root 3. Right? And then 125 is 5 times 25. 5's prime. 25 is still 5 times 5. And so I have a pair of 5's and 1 left over. So this is now 5 for this pair of 5's times the square root of 5 for that 5. Square root of 9 is just 3, just a number. And square root of 27 is 9, 3, 3, 3, so we got pauses here. And so that means the last term, which is minus, is 3 times the square root of 3. Okay, so now what we really need to do is just pair up everybody that goes together. So let's see what we have here. So we got 5 root 3. Actually, I'm going to do this by color. Let's see if we have any other root 3's in here. See, no. Ah, there we go. So I have 5 root 3 minus 3 root 3. So that's going to give me 2 root 3. That's those two. So that's taken care of, that's taken care of. And I just have these guys. And you notice this is a root 5. That's a root 3. They don't go together. So all I do is write it down. And then the 3, it's just plus 3. What if you write it in the other order, Mr. Ryan? You know, that's a good question. You know, these things don't really have like a set order. It's usually the order that makes things easier for you. Typically, when you write these things, if you have a term that's just a number, it either comes first or last, one of the two. Um, Other than that, there's really no set, hey, it has to be this way kind of a thing. So, yeah, you can write it in whichever order you want. Did I answer your question? Yeah. Okay, good. Um, Now, so that honestly, that is pretty much what there is to simplifying. There's not much more than that, or to addition and subtraction. Just simplify them and collect your like terms, or your like radicals, I should say. Okay, so we got that. Let's turn the brush back on. There we go. Now, when it comes to multiplication, so probably the most direct thing to do with multiplication is just a radical times another radical, right? Now, there's two ways to do these. I could start by just multiplying 5 times 15 and get the square root of 75, right? And then once I have that, I'll simplify it. Let's see here, that's 3 times 25. Oh yeah, we did this one, didn't we? Pair of 5s, this ends up being 5 root 3. Okay, now, there's a nicer way to do this. Because if this thing is going to be the square root of 75 anyways, I could kind of look at it this way. Okay, even if I don't multiply it out 5 times 15, all I have to do is imagine that there's some number up here, right? There's some number hanging out. And this is the first division of the factor tree. So 5 is already prime, so I can just bring it down. 15 is 3 times 5. And so let's see here. I have a pair of 5s here, and then I have a 3 left over. And so that gives me 5 root 3. And so when you're multiplying two radicals right next to each other like that, you can actually just pretend like that's the first branch on the factor tree and go through and factor it out. Or if you want to, you can just do 5 times, multiply the radicands out and just factor that what's left over. But notice, if I do the square root of 75, I didn't mention it when I first worked it out, but since I multiplied 5 times 15 to get 75 in the first place, I could just break it up to 5 times 15. 5's prime, that's what I did there. And then 15's 3 times 5, right? Well, let's circle them separate so they look separate. Is 3 times 5, and that's this piece. So I still get the same thing regardless. Okay. There we go. Now, when it comes to multiplying out more stuff, like if you have something like, oh, here we go again. Right, if you have something like 14ab to the third times square root of 21 a to the fourth b to the ninth, right? Let's think we're doing something crazy here. Again, you can kind of just think of everything together. So if we're going to start sorting this, one of the things we can do is just factor out both of these. 2 times 7, and then this one is 3 times 7, right? Okay, so I have a pair of 7s I can start with. So that means I have a 7 on the outside, and then 2 times 3 is 6 on the inside. So I've already taken care of the numbers now. Now I need to turn my attention to the variables, and I'm going to do it one at a time. So you notice here, I have 1a, and I have 4 a's over here. So that means I have 5 a's altogether, and I can simplify from that. If I have 5 a's, that means I can get 2 pairs out with a single a left over. right? And that's just dealing with all 5 of those together at the same time. Then with the b's, you notice I have b to the 3rd and b to the 9th. So that means I have 12 b's altogether. How many pairs of b's can I get out of that? 6. That's right, you can get 6 out of it. So this is b to the 6th. Are there any remainders? No. That's right, there's no remainders. So that means I'm not going to write anything inside. And so even without multiplying this out first, I can still come directly to the answer, right? And it's kind of nice working it out that way, to be honest. You could, of course, multiply everything together into a single radical. Let's see, 14 times 21 is going to be 140. No, that's not right. Let's see here. 40, it would be 49 times 6. 50, oh, there we go, 300. It'd be 296, I think. Right, so 14 times 21 is 296. Then you'd have an a to the 5th. So let's see here. That's 296. A to the 5th. B to the 12th. Right, and that's what you would end up simplifying if you multiplied first. You notice how big this number is. Oops, that's 294. My mistake. Right? But still, that's a pretty big number to deal with, and it's going to get messy. So it's a lot easier to just deal with the 14 and the 21. Because even if you multiplied it out, I know this is 14 times 21 in its first branch. Right? Okay, so that's how it starts. That's the most basic case, is when you have two things that, oh, what's that? You have two things that are just a single radical. Now, it turns out if you have other stuff, I did it again. Like if you have, you can do things like this, the square root of 5 times square root of 2 minus the square root of 10. Oh, excuse me. If I'm doing something like this, well, what does your gut instinct cry to you when you look at something like this? What does it feel like you're supposed to do? FOIL. That's right. Well, it's not really FOIL because I don't have two binomials. Distribute. That's right. You distribute. Good. So we're going to use the distributive property and just do two different multiplications. Square root of 5 times square root of 2 is the square root of 10, right? Because 5 times 2 is 10. Square root of 5 times the negative square root of 10. Well, I know this is going to be negative. I know that 5 is already prime and 10 is 2 times 5. And so if I just pair that 5 with that 5, I'll get a 5. And this leftover tells me it's root 2. Right? So I end up with root 10 minus 5 root 2. So we have to ask ourselves if we can simplify anything here. Are there any like terms that we can combine? And the square root of 10 is just 2 times 5. So we can't really simplify that. And then this one's simplified, and they don't have like radicals. So that would be your final answer. Right? It's pretty straightforward. They behave just like polynomials when you're looking at radical expressions. Okay. Now, one of the things that we are going to be looking at, and I'm going to put two problems on here. And when I put these problems down, I want you to go ahead and pause the video and see if you can work this out. Right? I want you to see what you can do. Follow your gut. See what your gut tells you, and then once you have an answer or once you get to a point where you're stuck, go ahead and play then. Okay, so let's see here. How about root 2 minus the square root of 3 times 2 plus the square root of 3. Okay, so that's one to play with. And then the other one we'll play with is the square root of 7 minus the square root of 5 times this, that's not what I meant, square root of 7 plus the square root of 5. Okay, so go ahead and pause. Okay, if you're still watching, then you've either paused and already done your thing, or you're just going to blast straight through it. So, what does it feel like we should do here? Oh, now we can FOIL. That's right, now we can FOIL. This is the situation that allows us to FOIL. In fact, technically, anytime you have a binomial term times another binomial term, FOILing is a typical good way to go. And so let's go ahead and multiply this out. Actually, let's switch to blue. So 2 times the square root of 2 is going to give me 2 root 2. Root 2 times root 3 is going to give me root 6. Negative root 3 times 2 is going to give me negative 2 root 3. And negative root 3 times root 3, well, that's going to be root 9, which is just 3. So there's a bonus here. If we're taking a root and we're going to multiply it by itself, it cancels the root. So I just have a single number here. And so if we look at this, I can see that none of these simplify, and none of them are like terms. And so this is my final answer as far as that goes. That's as far as I can go with this one. Now, let's go ahead and look at this second one here. Let's go ahead and multiply this out. Remember, we had said anytime you multiply a root by itself, it kills the root. And honestly, what you're really doing is you're squaring it because you're multiplying it by itself. So squares undo square roots. Okay, so root 7 times root 7 is 7. Root 7 times root 5 would be root 35. Minus root 5 times root 7 is minus root 35. And minus root 5 times root 5 is just going to be minus 5. And so you notice something here. That middle term, they kill each other, right? They're positive and negative of the exact same thing. And so all I'm left with here is 7 minus 5. And so what I just got was 2 for that particular answer. Right? So some of these really simplify down quite a bit. Right? And that's actually important. This particular property is very important. And it turns out that anytime you have two things like this, where you have plus and minus the same radical expressions, right? You know, root 7 plus root 5 times root 7 minus root 5. Each of these terms, or each of these factors, actually they're not terms, they're factors. If the terms are positive or plus and minus of the same thing, right? The operation has changed between them, then these are called conjugates. These are conjugates of each other. And conjugates have the property that when you multiply a number by its conjugate, you will always get a whole number. You will get something that does not have a radical in it. This is going to be an important thing to note when we're doing the division part, right? That's a pretty important thing to happen. Okay, now, this is the other thing I wanted to show you, because this may or may not be new to you. You are by no means obligated to do things this way, but this is kind of a nice way to multiply things. So what I'm going to do here is I'm going to take this, I'm going to redo this problem here, but I'm going to use a different multiplication technique besides FOIL. This is called the rectangle. If you've taken my class before, you've seen this. I actually came across this the first year I was teaching high school. And ever since I did this, I pretty much do all my multiplication this way. So here's the deal. You write one term across the top. It doesn't matter which one. And or one factor across the top. The other factor you write across the side. And what you do as you go through and fill this out is each one of these boxes is filled with the product of what's on the edge of it. So these two things together fill this box. Root 2 times root 2 is 2. Oh, you know what? I just wrote down that problem wrong. Let's try this again. Let's back up one. Undo. That's what I want. Let's go ahead and look at this again. Okay, got it. I looked at that as a root 2 instead of a 2. This is just a 2 here. Oops. There we go. Okay, so if we try this again, 2 times root 2 is 2 root 2. 2 times minus root 3 is minus 2 root 3. Root 2 times root 3 is root 6. And minus root 3 times root 3 is minus 3. And if you notice here, these are actually all of the same terms I have up here. And all you have to do now is write them down. What's nice about this is this gives you a nice in-between step for collecting like terms and things like that, because it makes it a little more obvious that they're there in the first place. So, yeah, as you go across this, the things that go in this square would be this times this. This square is going to be this times this, right? And we just end up filling it in that way. It's like the old style multiplication tables, but I do a lot of my multiplication this way just because it's a lot easier to keep track of things. It's also easier to trace your mistakes backwards if you make one. And that'll work over here too. What I would suggest is try multiplying this out using this box method and see if you get 2. If you don't, okay, as long as FOIL works for you, keep going. I would encourage you to at least attempt the box method though. Okay, now I want to get on to the last topic. Okay, now, so we have listed here, I have one more section to cover, but I think what we're going to do, because I just looked at the time on this video, we're closing in on an hour here real fast. So I think what I'm going to do is go ahead and break this off. We're going to put the rest of it in a second video that will be attached to this. And then I also realize that there is one more thing, because this has to do with the bad handwriting in my own notes, but there's one more thing that I didn't list, which is rational exponents. And we're going to push off rationalizing the denominator and rational exponents for the next part of this lecture. So we're going to go ahead and call it quits right here. Thank goodness. I know, right? It is getting long. So in any case, look for the next video, and I'll see you there.